So continuing with some max-min problems, and the interesting thing about this one is there won't be any numbers in here, right? Like this is, we're going to come up with an expression in terms of basically a couple of, and they're not variables, they'll actually be constants, right? So that window consists of a blue semicircular section surmounting a clear rectangular section as shown below. The blue glass lets through half as much light per unit area as the clear, so clear glass, blue glass. Determine the radius R of the window. So there or there, that's R. That emits the most light if the perimeter of the window is K units. Okay, so the perimeter and the value of K, so let's call this H. Then this here will be 2R. And this will be H. And this will be what? Yeah, it'd be like half of 2 pi r, right? Because it's the perimeter of a semicircle. Okay, so that means that we can get an expression for perimeter. And the perimeter of the window is K meters. Okay? All right, so what are we going to say? Let's start off by saying that P and K are constants. And so the amount of light, move that down a bit. So it's based on area, right? Or, I mean, the amount of light coming in. So we've got area. So the area of the rectangle is 2RH. And the area of the circle is 1/2 pi r squared. Okay. Now, if the perimeter is K, then we know that we've got H, we got 2 H's, 2 R's, and a pi r. So 2H plus 2R plus pi r is equal to K. Okay, so that's our perimeter. Okay, so we got H, this is 2R, right? Because that's R, so then this length is 2R's, right? That'd be the diameter of the circle there. And we want perimeters, so we got H plus 2R plus H, so 2H plus 2R, then half of a circle, which is half of 2 pi r, or just pi r. Okay. Now, if we solve that for H, so H is equal to K minus 2R minus pi r over 2. And we're now going to substitute that in here, right, for A. Well, let's simplify what we've got here for L, so the amount of light coming in. So we've got P over 2 pi r squared plus 4 PRH. Okay, so let's get rid of the H. We're going to do that by substituting this expression. So we got P over 2 plus 4PR times K minus 2R minus pi r over 2. Really? Oh, really? Oh, damn. It's like, it's never easy. All right, so where are we now? So let's simplify what we got here. So P over 2 pi r squared, that 2 goes in, so we got plus 2PR and yeah, it's a good sort of thing of don't lose plus signs or minus signs when you're doing work. Like all of a sudden they're gone and there's 2 brackets and now you're multiplying and things get pretty bad actually at that point. Let's expand. plus 2 PKR minus 2 PR squared. Oh, that's a 4, sorry. Minus 4 PR squared minus 2 pi PR squared. Okay. Oh, I never told you what P was, right? It's P. Suppose should say this stuff, right? Didn't say up here. So let P be the amount of light. Per square unit of the blue glass. Okay, sorry about that. I should define. I thought it was in the question, and it's not. Okay, so K is there. I mean, seriously, K should have been, and then P should have been the perimeter. So I don't know. Bad choice of variables, I guess. But yeah, write that in, right? So P is the amount of light per square unit of the blue glass. Right. So we've got P times the area of the blue glass. The clear glass lets in twice as much, so 2P times that area. Okay? Sorry. All right. I thought I was in the question, and this I was looking at. That's not in the question. Okay? And P and K are constants, right? The amount of light that's let in is a constant. Man, I wish I could rewind that stuff. Okay, so what do we got? We got that. And is there anything, well, we got a p pi r squared here, and we got a p pi r squared here, right? So these guys are like terms. So I've got a half of something minus 2 of something, which will be minus 3 halves of that. So let's do that. Minus 3. So let's go minus 3 halves pi p r squared. And yeah, that's it for stuff. So minus 4p r squared plus 2 pkr. Okay, so let's do that. And now we're going to take the derivative with respect to r, right? So L prime. So multiply by 2, so negative 3 p pi r minus 8 pr plus 2 pk. So that exists for all values of r, right, that we could imagine.
Why is it?
So I've got the p over 2 here, right? So this is a half p pi r squared, and this is minus 2 p pi r squared. They're like terms. So these guys. So I've got plus a half minus 2, which gives me minus 1.5, which we write as minus 3 halves, right? Okay. So that's where that came from. This and this just carry down. We're taking the derivative with respect to r, so multiplying by 2, we get that. And the 2 here, and get rid of the r. So, L prime exists everywhere. Of course, I can't do that. So, L prime and L prime equals 0 means that 0 is equal to negative 3 pi pr minus 8 pr plus 2 pk. And basically what we're going to do is we're going to solve this for r, right? We want to know what is the radius when. Okay. You notice all the p's? They all got p's, so we can divide both sides by p. Okay. So let's do that. So 0 is equal to negative 3 pi r minus 8r plus 2k. Okay, so it doesn't depend on the amount of light that's being let in. And let's get these guys over here. So 3 pi r plus 8r is equal to 2k. Factor out the r. So r is equal to 2k over 3 pi plus 8, right? So if we know the perimeter that we want, then we set the radius equal to this number. Now L is a quadratic function, right? If you look back at L, it's in R squared and R. It's got a negative leading coefficient, right? Negative 3 pi p over 2r squared minus 4 p r squared, which means it opens down and has a maximum. Okay, so let's write that in, right? So since L is a quadratic function, with a negative leading coefficient, attempts to spell coefficient, attempts to write it. Coefficient. We know there's a local max. Okay, so we know there's a local max when r is equal to 2k over 3 pi plus 8. And it seems I have to move stuff this way. So the most light is let through. When r is equal to 2k over 3 pi plus 8 meters. It's kind of a more general solution, right? We're not actually coming up with a number and saying, hey, we're coming up with an expression, though. Those are the best kinds of solutions, right? A more general solution allowing you then to say, well, if I want to make it this big, then this is how big I should make the radius. All right, move over here so I can actually move it. Why is what? Meters. Okay. Boat A and boat B, and they're moving away from. So this applies to boats and trains and automobiles and where. I mean, in this case, they're moving perpendicular to each other, but because we're not doing trig stuff, right? If we want them to move at an angle to each other, then we got to use cosine law and stuff to figure out distance, right? But if they're moving perpendicular, then we can use the Pythagorean theorem. So we got boat A is 40 kilometers west of boat B. So there's A and there's B. And which way? Boat A is sailing east. Oh, hang on. Let's move A. So there's A and there's B. And this is 40 kilometers. Now, boat A is moving east, so it's going this way. And boat B is starting at the same time, goes north. So there's B. And here's the distance between them. And this distance here that boat A sails is 20 times t, right? Because it's going at 20 kilometers per hour. So t will be the time in hours. So let's say that t be the time in hours since the boat's sailed. So at time 0, they're here, and then they start moving, right? And B is moving, so this distance here is going to be 10t, right? 10 times time. So just imagine in 1 hour, this will have moved 20, and this will have moved 10. And then what's this distance here? Well, it's going to be 40 minus 20t. Okay, so we got 20t, we got 40 minus 20t, we've got 10t, and the distance between them, okay, at some point t, or at some time t. And what do we want to do with that distance? During the time when the boats are closest together, okay, so we want to minimize d. So using Pythagorean theorem, right, because they're going north, it makes life a lot easier. We don't have to, if they're moving at different angles, then we got to get trig in there, right? Because we'll have to use cosine law to find the distance. But you don't, well, you could do that, right? It's the same idea. It just becomes a little more complicated expression. But right now, it's an easy expression, right? So d squared is equal to 10t squared plus 4t minus 20t squared. Okay, so that's simply using the Pythagorean theorem, right? So d squared is equal to 100t squared plus, okay, now we got to square this, which means we're going to end up with how many terms? 3, right? Good, yeah. So we square the first term, 1600. We multiply the two together, giving me minus 800. We double it, so we get minus 1600t. And we square the last term, which of course must always be positive because you're squaring it, and that'll be 400t squared. Barely squeezing it in there. So here's what we're going to do. We're going to let big D So same idea. We did this the other day, right? I think with related rates or something. If we're going to minimize d, if we minimize d squared, if we get the smallest d squared that we can, then we also have the smallest d that we can, right? Okay. So that's why we're going to just work with big D, which is d squared. Okay. And I can't move it that way, can I? And we're going to go over here and drag this down. Okay, so d prime is 1000t minus 1600, which we can factor as a factor of 200 there, so that's equal to 200 times 5t minus 8. D prime exists everywhere, right? It's just a linear function. Everywhere. So d prime exists everywhere, and it's equal to 0 when t is 8 over 5, right? So, yeah, or you could say d is a quadratic function, it opens up, therefore it's got a minimum, and there's your minimum. But let's do our little chart. We usually do a little chart, right? So our time starts at 0, and we've got a time of 8/5, and we've got two factors, 200, 5t minus 8, tell us about d prime, and tell us about d. So 200 is always positive, right, because it's 200. 5t minus 8, it's going to be negative here, and actually, wait, this should be the 8/5 here. Why am I drawing the line there? Positive there. D prime is negative, and then positive. So We have decreasing and increasing, giving us a local min at that point, right, at 8/5.
Don't you know that from like the quadratic one?
Yeah. Or since D is a quadratic with positive leading term, actually it's coefficient. Let's see if I can actually write it this time. Okay, so we know we have a local min. It occurs at a time of 8/5, which is 1.6. So the boats are closest together. After 1.6 hours. Yeah, oh wait, I wanted to go down. So if we plug that in, if I want to know, so what is that distance, right? It's going to be the square root of the d squared formula. So it's the square root of 40 minus 20 t, which is 1.6 for t, right? Plus 10 times 1.6, so 10t squared. 20 times 1.6 is 20 is 32, okay, so we get 8 squared. And 10 times 1.6 is 16, gives us 16 squared, which is 64 plus 256, which is the square root of 320. And I don't know what the square root of 320 is, and nobody does, because it's, but it's less than 6. Well, wait, what's 32? It goes 16 goes into that 200 times. No, wait. Too much math. 32. 16 is a perfect square, right? It's 16 times 20, but then 20 has a 4. Oh, it's 64 times 5. So it'd be 8 root 5. Anyway, in any case, it's less than 40, right? Because we know that they started out 40, and you want to examine the starting condition, because maybe they were closest together at that point when they were 40 apart, but no, because this is less than 40. Okay, so it says really is the minimum. So remember, at sometimes we have to look at the extremes. There is no outer extreme, but they're just going to get further apart. So, but we need to make sure that it is less than the starting point. Okay, so we're good. And we'll ask you, when we ask you questions like this, we'll make sure the numbers don't require a calculator. Right. So some numbers I'm going to give you in the next example are ones that you can only really get with a calculator, right? But we'll keep it so that they're workoutable without a calculator, right? Or able to be worked out without a calculator. Oh, I left 2 pages and I didn't need to. Edit. Delete page. Here we go. A cable TV company is laying cable in an area with underground utilities. 2 subdivisions, P and Q, are located on opposite sides of Willow Creek, which is 100 meters wide. Not exactly what I would call a creek. You know, I mean, 100 meters wide creek. Like creeks are like, you know, you can step over creeks a lot of the time. Yeah, I don't know, man. That's like a river or something. That's a football field. Anyways, the company has to connect points P and Q with cable, where Q is on the north bank 1,200 meters east of P. Okay, so here, let's draw a little diagram here. So here's Willow Creek, or river. And we got points P and Q. And we know that this distance is 1,200 meters. We know that distance is 100 meters, and it costs 40 meters to lay cable underground and 80 meters to lay cable underwater. Determine the least expensive way to lay the cable. It's actually like a problem that could exist in real life, right? So I mean, we could just lay it all underwater, and this distance is pretty easy to work out, right? It's the square root of 100 squared plus 1200 squared. We could go all the way on land to here, and then go 100 meters here.
Right.
Okay. So those are two extremes that we got to look at. What if you just go here, and what if you go straight across and then down, right? Because those are two possible costs. And then we're going to work out an expression for, so what if you go partway along here and then you cross? Okay? So partway along here is we're going to go to point R. So we're going to lay underground from P to R, and then we're going to cross the water. So if we do that, we're going to have a distance here, which we will call x. The distance between P and R will be 1200 minus x. And this distance here is, of course, 100. And then we've got this distance here, right, which we'll call y. So we're going to let C be the cost of laying the cable. Now we know that this number x is somewhere between 0 and 1200. Okay, if x is 0, then we're just going 1200 here and 100 here. If x is 1200, then we're not going there. We're just going across here, I guess. Okay, so it costs $40 to lay the cable from P to R, right? So the cost, or $40 per meter, is 40 times 1200 minus x. So that'll be the cost of laying along the ground, plus 80 times y, which is the cost of laying underwater. But we know, or we're going to squeeze in this little box here, that y squared is equal to x squared plus 100 squared. And so y is equal to the square root of x squared plus 10,000. Okay, so we could substitute for y an expression with x. Right, makes life easy. So C is 48,000 minus 400x minus 40x plus 80 times the root of x squared plus 10,000. So there's our expression for cost simply in terms of x. So we want to minimize the quantity, right? So we're going to take the derivative. This is gone. We get minus 40 plus 80 times 1/2 times x squared plus 10,000 to the negative 1/2 times 2x, right? So we've got 80, which is just the constant, and the derivative of this, right, which is 1/2 times that to the negative 1/2 times 2x. Simplifying. So the 1/2 and the 2 take each other out. We got an 80x over the square root of x squared plus 10,000. Since x has to be greater than or equal to 0, right, it really doesn't matter. That's x squared plus 10,000, so that always has the square root, right? I mean, the lowest it could be is 10,000. So C prime exists everywhere. You can't make that 0. I'm not going to calibrate it. We're almost done. Okay, C prime exists everywhere. And C prime is 0 when 0 is equal to negative 40 plus 80x over the square root of x squared plus 10,000. So we're going to solve that. So let's move the 40 over. And let's cross multiply. And divide by 40. And square both sides. And solve. Okay, and so there's our solution, right? So we square root both sides. The square root of 10,000 is 100. We've got that root 3. If you like, we could write it as 100 root 3 over 3. And now what we're going to do is kind of look and say, well, we've got 3 intervals here. We've got 0, 0 to 100 root 3, and then over 100 root 3. And so let's take our number line. It's going to call that 100 over root 3. And what was C prime? So it'll be negative here and positive here, which means that it's decreasing and increasing and has a local min. So the local minimum occurs at 100 root 3, or sorry, 100 over root 3, or 100 root 3 over 3. So we now have to test the endpoints, right? We have to say, what is the cost if x is 0? So that's, okay, we'll just back this up a smidge. So what is the cost if this is 0, this distance is 0? What is the cost if this distance is 1200? And so one of those will be just straight across here, one will be here, and then the other one is what's the cost with the 100 root 3. Okay, so test the endpoints. Or test all values. So if x is 0, it means we're doing all 1,200 meters along the south bank, and then we're crossing over. So it would be 40 times 1,200 plus 80 times 100. Which is 56,000. Okay. Again, and we give you on a test, the numbers will be easy to work out, right? We'll make sure that the problems have numbers that are easy to work out. The cost of the other endpoint, so if we have 1,200, which means that we're just going straight across the river, right? So if all we do is go straight distance from P to Q, straight across the river, then that works out to, and I'm just going to give you the number, 96,333. I mean, obviously that has to be more expensive, right? It's most expensive to lay the cable underwater. And if C is 100 over root 3, okay, so that's 54,928, which is the minimum. Okay, so remember in this case we have to examine the ends and the in-betweens, right? See if an end is cheaper.
Why do you have to do like the endpoint?
Because we don't know if the cost of just running it straight across is the cheapest, or the cost of going all the way and then across is cheapest, or doing part of each, right? So we have to look at all three costs, okay? Because we can't be sure. Oh, because you know, remember we're dealing with, you know, we did the absolute minimum or on an interval. That's what we're looking at. We're looking at an interval where x goes from 0 to 1200. Anytime we examine an interval, we have to do the endpoints of the interval and then the point in between, because maybe the lowest point is one of the endpoints. Okay, we don't know that. You know, even though we know it's like a, is it a quadratic? No, it wasn't even a quadratic. Okay, so what are we going to say in conclusion? The least expensive
with X calculated this but he needs